Hi. So today let's continue our math camp and discuss several concepts which are important in our further studies. Okay. So the first concept that we're gonna introduce is the set. Okay, and this is the basically the very fundamental concept in mathematics, right? So set by a formal definition is that set is just a collection, or it's just a lot of, or like a group of different things, okay, or different objects. So a set, it has so this definition is not very rigorous, right? So it's just it's pretty intuitive, and this is the definition of set, okay. But it's just it addresses some fundamental properties of the set, right? So it first is saying that it's a collection or it's a group, so we have to put those together, right? And another thing is that we have those things to be different, okay. So the things, all those things in a set, they have to be different from each other. Okay, so for example, a set could be some numbers 1 2 3, or it could be some colors, red or blue, okay. And so we denote the empty set to just using the curly brackets, or just this capital letter phi, but this is just a notation this for this empty set, right? So this is actually not some any letter. Okay, so and we say that if we only have one element in some set, we call that as a singleton, right? And we have the relationships between the set, and which is this subset and superset, right? So subset says that so some set, all those elements, they're also contained by some larger sets. Then we call this smaller set would be a subset of the other one, okay. And we can put a another line under this notation to denote that those two, they can be equal to each other, okay. But here they're not equal. So okay, and so empty set would be a so this is the true subset, right? So the other one would be also including the equality, okay. So we say that empty set would be a subset of any sets, right? So it's just whenever we write the sets, we do not write empty set if we have some non-empty elements in the set, right? So that empty set is always a subset of every set, okay, all the sets. And of course, the set itself, it is a subset of itself, right? Okay, so when we're talking about the cardinality, it's just the number of the elements in the set. Okay, so if we have just one element, then the cardinality of that will be just one. Okay. Okay, and we use the calligraphic letter to denote the set of sets or a family of sets. So here we have those A and B as some sets. So you simply put those together and to be a new set, okay. So it's just I just put extra brackets to denote that, okay, those are just sets, okay. Okay, so and when you say that the power set of some set, that'll be we can either use p of s or use 2 to the power of s. This is not an operation, because it is just notation, okay. So 2 to the power of s or p of s, that would be the power set of some set. So for example, if we have the set to be including 1 and 2, so the power set includes all the subsets of itself. So it could be empty set or set of 1 and 2 or 1 and 2, okay. So that's the power set. Okay, so next we're gonna introduce some basic operations of the sets. So if we have set A to be 1 and 2, B to be 3 and 4, so a union of A and B, that would be a set including all those all the elements from A and B. So that would be everything here, right? And the intersection, that would be the empty set, since we do not have any common elements from A and B. And when we write this A excluding B or A minus B, or this is just the difference between A and B, okay? So because we want to just remove the 3 and 4 from set A, but A doesn't have 3 and 4, right? So it's just still 1 and 2. Okay, so and when we say that a Cartesian product, so or it's just normally we call this as cross product, so that'll be for those two sets A and B. So we simply put all those corresponding elements pairwise and put them as the new set, and list all of them as the elements in the new set. Okay, so that'll be just pull one of each from either of A and B, then put them together as the new element, and put all of them together. Put all of them here, okay, as the new set. That'll be the Cartesian product or the cross product. Okay, good. So and the next thing for today, that'll be, we're going to talk about this Euclidean space. Okay, and that'll be the very intuitive and simple space that we're gonna work on for a lot of studies, right? So intuitively, the Euclidean space is just some space or some so we're not gonna define the space, right? So space is just like a place that is that can be represented by some vectors. Okay, so here the space is just in the Euclidean space is intuitively that would be the space with the metrics that those metrics that are using the straight distance. Okay, so whenever we have 2 points, we want to measure the distance between 2 points, we simply connect a straight line, no matter it's 1D, 2D, or 3D. Okay, or even it's in higher dimensions. We just use the straight lines to measure the distance. Okay, so that would be the Euclidean space. So, and in a formal definition, we say Euclidean space, that would be a space of vectors of real numbers with n components, and we simply denote that as Rn. Okay, and here this D, when we say that this Rn, that would be Euclidean space, and we use this D as a Euclidean space metric, and for some 2 points x and y in the space, and we're gonna use this D as the metric or the distance of this 2 points. That'll be just the square root of the summation of all those squares of those distance in each dimensions. Okay, good. So, and we're gonna have some notations for the points in the with many dimensions, right? So we're gonna say that x, and this would be in the Euclidean space, right? If we're gonna say that x equals y, then this would be we're talking about so this is if and only if for each dimension we have all those dimensions, they are equal to each other, right? And if we say x greater than or equal to y, then this means that for all the dimensions pairwise, then the x is greater than or equal to y, right? And if we say that x greater than y, then it simply means that for each dimension, for all the dimensions, we have pairwise xi is greater than or equal to yi, but for some dimension, we have strict inequality here. But if we put double greater sign here, so that simply means pairwise or dimension-wise, we have xi greater than yi for each dimension. Okay, so those are just some notations when we compare the vectors or the points in the Euclidean space, right? Okay, so next we're gonna introduce another concept defined in the Euclidean space and using the set that we called epsilon ball or epsilon open ball. So you can also similarly define an epsilon closed ball. So that would be the opposite of open, but normally we just use open here. Okay, so for some point in the Euclidean space with n dimensions and some real number epsilon, so we're gonna say that epsilon ball of x that would be just the set where we have this y also in the Euclidean space. So where we have the distance between x and y, so that would be the distance smaller than some number epsilon. Okay, and we call this just this ball of x with this radius of epsilon, right? And that would be a ball in 3D, but in 2D that would be just a circle, right? Okay, so and next we're gonna introduce some notations where we are gonna use to represent the greatest or the lowest values of some set. Okay, so we're gonna say that for some set A as a subset of root number, we're gonna say the maximum of the set A if this x will be just the greatest value of in this set A. Okay, but something important to notice is that this x element has to be within the set of A. Okay, if we sometimes later we will shortly see that sometimes we might not have a maximum or a minimum. Okay, and that's simply because that the set doesn't have so the sets they're not closed, right? So they're if they're open, then they might not have the maximum or the minimum. Okay, so correspondingly, then we say that minimum of set A. So that the definition would be that if we have this element also in the set A, that would be the smallest one. Okay. Okay, but sometimes that we just mentioned maximum or minimum, they might not exist, right? For example, if we have on the both two sides, we are open on the two boundaries, right? So here we cannot use the maximum or minimum because the 0 and 1, those two values, they're not in the set A. So we're gonna use two alternative definitions. The first one corresponding to the max, that would be the supremum, and the other one for the minimum, that would be the infimum. Okay, so when we say that the sup of A, that would be the least upper bound of A. Okay, so it's pretty similar to the maximum where we have x greater than or equal to A, but we're gonna have that. So this will be the upper bound, but we also have to let this be the smallest one, the smallest upper bound. Okay, so we have an extra requirement for any y such that if y also greater than or equal to A, then this x has to be less than or equal to all those possible value y's. Okay, and then correspondingly, similarly, we define the inf of A. Okay, that would be the greatest lower bound if we do not have a minimum for some set A. Okay, all right. So next, we're going to define some very useful concept called open set. Okay, so previously we used the notation for the open set, but we haven't defined that yet, right? So open set, that would be that by definition for some set S as a subset of Rn, that would be an open set if for all those X elements in the set S, there exists an epsilon where this epsilon ball or this epsilon open ball, that'll be also a subset of S. Okay, so intuitively here we have a little figure for us to help us understand this further. So we have this dashed line as sort of so-called boundary, quote unquote, but that's because we cannot reach the boundary, right? It's open. But by notation, by the definition here, the open set we're gonna have some, we can always find this, there exists this such epsilon, right? We can't just draw a circle or a ball surrounding this, around this point X, right? And here, no matter how close we are to the boundary, quote unquote, then we can always find even a very small epsilon open ball, right? Because we cannot reach this boundary, and in the even if it is very close to this so-called boundary, but we can always find a very small epsilon to make this happen, right? So that would be the definition for the open set. So we have some properties for the open set. So the first is that the empty set and the Rn itself, they're open, okay? And the union of any open sets is open, and the intersection of finite open sets is open, okay? So we're gonna skip all those proofs, and you can find those by yourself, or you can try to prove those by yourself, but we're gonna just skip those proofs. So an interesting example of the third one, or actually a counterexample, is that example of infinitely many of the open sets intersection that is closed. Okay, so let's see an example of this. So we're gonna have, instead of 0 to 1, we're gonna have, the first thing we're gonna notice here is that we have those open boundaries. Okay, and the next thing is that instead of 0 and 1, we have something extra. That would be the 0 minus 1 over x and 1 plus 1 over x. So where we have those x from 1 to up to infinity. Okay, so intuitively from this line, real line, then we can see that as x goes from 1 to up to infinity, and then this we have this bracket, and they're coming closer and closer to 0 and 1, right? They're approaching to 0 and 1. So why we're saying that this, in as x goes to infinity, this actually the intersection of the family of those sets, it is closed. So the first part is the, for example, we're gonna see for 0. Okay, so it will be exactly the same for 1. So for 0, and the first thing is that we have this minus 1 over x. Okay, and that has to be, because x is always positive, right? So that has to be always less than 0. That has to be always negative. And when we're taking the limit as this x goes to infinity, then this minus 1 over x, that goes to 0 minus, right? So there's 0 minus means that would be the left or the negative side of 0. Okay, that's the direction of this limit. So when we have that, the second part is that we have this open bracket, or this bracket that is not including the boundary, right? So that means we're gonna take the other side of 0 minus, or the 0 negative. So that'll be the other side of that. That'll be not only 0 plus, but also the 0 itself, right? So that's why we combine those two as the closed of 0, right, for this boundary. And that would be exactly the same for 1. Okay, so but this is only true for the intersection, because the intersection that takes just the common elements, right? So that would be the 0 to 1, this smallest, this most inside part, right? But for the union we just mentioned, we do not need this, right? Because for the union we don't take the most inside one, right? We take actually the just every element that we have for each of those sets, because that is union, right? So for the union we do not have to worry about the infinity. Okay, so that would be still open for the infinity many of the open sets if we're gonna take a union, right? All right, so the last thing we're gonna talk about today, and that will be called topology. Okay, and that's also very useful later for us to define some further concepts. Okay, so topology, intuitively, it means that after some operations, okay, some certain operations, we're gonna still in the same place where we start from. Okay, or we're gonna still in the same place, or still in the same topology. Okay, so that's the idea of this topology. So it doesn't matter whether we take those certain operations or not, we're still in the same place. Okay. And there are many of those definitions for topology, but we're gonna just here to use the open sets to define for this concept. Okay. So we're gonna say that a topology on set X, that'll be a collection tau of subsets of X. So a topology is just a subset of X. So that's it. it just has some requirements. Okay, so the first requirement is those have to be open sets. Okay, and so that's why we're gonna have some similar requirements that we see before. Okay, and it also satisfies the first is that the empty set that will be an element of tau, and X itself also has to be an element of tau. Okay, and the second will be very familiar, and third one also. So the second will be that any union of members of tau belongs to tau. And the third one is the intersection of finitely many of those members of tau belongs to tau. Okay, and the topology, and later we'll see that that'll be very useful for us to define the algebra or sigma algebra later. That'll be very useful. Okay, and we can also use, normally we use the open sets to define those things, but of course you can always, alternatively you can just use closed sets, or later we'll define the closed sets. That'll be just the opposite of open, right? So you can always use closed sets to define things, but they're just almost the same, but not quite. There are some minor differences when you are changing the definitions from open to closed. Okay, and that'll be from the Morgan's laws. Okay, that not be difficult. You can check that by yourself. So, and here we're gonna have a very simple example of a topology. So let's say this X set would be the set of 1, 2, 3, and 4. So some taus we could have first a pretty trivial case that would be the set with just empty set and X itself. Okay, so whenever we gonna take all those, so the topology here, we have to satisfy all those requirements, right? You can verify this by yourself. And another extreme case that would be the power sets. Okay, so we can have all the possible subsets of X itself to throw that into the set tau, and that'll be also a possible topology. And some intermediate or some middle, somewhat general topology of the set X is here as example. We have empty in 2, 1 and 2, 2 and 3, 1, 2, 3, and X. Okay, so we can always see that empty and X itself, they have to be inside of the topology. And it's just instead of those two extreme cases, here we have those things, those elements, and you can verify by yourself that we can always satisfy those requirements if we're gonna have those elements here. Okay, no matter you're taking the unions or the intersections. Okay, so they're still belonging to the topology itself. All right, so that'll be everything for today. Okay, good.